In this video, our goal is to build a design-led strategy for selecting materials and processes. That means we begin with that need of design itself, using those requirements to guide our choices. But to do that, we first need to understand the design process. Design begins with the market need. That need is analyzed and turned into a set of design requirements. From there, ideas called concepts are explored, developed, and refined into a detailed product specification. Material and process choices aren't separate, they evolved alongside this development. With that foundation, we can move into a structured selection strategy. It unfolds in four key steps: translation, screening, ranking, and documentation. There are two types of design: the original design and a redesign to the original design. Original design begins with a fresh idea, something entirely new. It involves building the information and system needed to bring that concept to life. Evolutionary design, on the other hand, starts with an existing product and refines it, boosting performance, cutting cost. Sometimes the demand of a new product leads to the invention of entirely new materials. Nuclear power led to the creation of zirconium and advanced stainless steels. The space race drove innovation in beryllium alloys and lightweight composites. And today, turbine engines push the boundaries of high temperature alloys and ceramics. But this is not always the case. Design always begins with a need or a bold idea and ends with a full product specification. But no need can be met unless it's clearly defined. That's why every design journey starts with a simple focused statement. A device is required to perform task X. This becomes the foundation of a clear set of design requirements. In the conceptual design stage, all possibilities are on the table. The designer explores different concepts, experimenting with how they can be combined or separate to meet the design goals. Once promising ideas are identified, the process moves into the embodiment stage. In the embodiment stage, the concepts are analyzed in more depth. Components are roughly sized and clearly choices of material and processes are made to understand the performance and cost implications. This stage results in a workable layout, which then feed into the detailed design phase. In detailed design phase, every component gets fully defined with precise dimensions, specifications, and often mechanical and thermal analysis. Optimization techniques are used to fine-tune the system for maximum performance, minimum cost, and safety. The final materials, geometries, and production methods are selected. By the end, complete product specification is in place. Now let's talk about redesign. It's worth noting that most design work isn't about inventing from scratch. It's a redesign, building on existing products, solving problems, improving performance, and cutting cost, without changing the core principles or discarding well-functioning parts. Redesign often begins with a problem, and there are several scenarios that call for it. The most urgent is the product recall situation. If a product on the market fails safety standards, redesign becomes critical. Often, the root cause is a material failure. In such cases, a new material must be selected, one that keeps the strength of the original while fixing its flaws. Then, there is a poor value for money scenario. The product may be safe, but its performance doesn't justify the price, prompting a redesign to improve a function or efficiency. Since much of a product's cost comes from materials and processes used, the solution is often to rethink both with cost cutting in mind. Another common driver is competition. In fast moving industries like consumer electronics or automotive, new models are rolled out every year or two. To stay ahead, companies must continuously refine and innovate, often through material or design upgrades. But the role of material doesn't stop once production begins. Product can fail in real world use, and every failure tells a story. Wise manufacturers gather and analyze this data. It often reveals a mismatch between material and use, something that smart redesign can correct. The choice of process is closely tied to a material. The material's formability, machinability, weldability, and heat treatability all affects what processes can be used. At the same time, the requirements for shape also influence process choices because the process defines not just the geometry but also the size, precision, and cost of component. It's a two-way interaction. Specifying a shape can limit your material and process options, and choosing the process can limit which material and shape are possible. The more complex the design, the more tightly these factors are linked. At the center of all this lies the crucial interaction between material, process, and shape. And to manage it effectively, we need design strategy. That strategy has four key steps: translation, screening, ranking, and documentation. Selection begins with finding the best match between the what a design need and what materials and processes can deliver. Keep in mind that materials and processes must be compatible. The first step, translation, is about turning a design requirements into technical languages, identifying constraints that must be met and objectives to optimize. This act as a filters. Materials that pass the constraint and perform well on the objectives moves forward. Next comes screening, eliminating all the materials that don't meet must-have criteria. Then, in ranking stage, the remaining candidates are ordered based on performance metrics like cost, weight, or strength. Finally, we dig deeper into the top choices. We look at how they are used today, how to design effectively with them, and what case studies, both success and failures, can teach us. The last step is called documentation, and it completes the selection process. Every engineering component is built to perform one or more functions, whether it's supporting a load, containing pressure, or transferring heat. But achieving that function comes with constraints. There may be a fixed dimension, limits on how much load part can carry, or requirements to conduct or insulate against heat or electricity. The component also has to perform within specific temperature range and environmental condition. Within these boundaries, the designer still has some freedom. Dimensions are not fixed, but constraint can be adjusted. And most importantly, the designer is free to choose the material and processes to shape it. These adjustable factors are called free variables. It's essential to understand the difference between constraints and objectives. A constraint is a non-negotiable requirement like minimum strength or maximum operating temperature. An objective, on the other hand, is something you aim to optimize, usually by minimizing or maximizing a specific property like cost, weight, or performance. For a super light spring bicycle, the main objective is to minimizing mass while keeping cost within a limit, making cost a constraint. But for affordable city bike, the roles are reversed. The goal becomes minimizing cost, and keep weight below a certain level is now a constraint. Screening helps narrow the field by eliminating materials that simply can't do the job because one or more of their properties falls outside the required limits. These limits, known as attribute limits, come directly from the design constraint. For example, If a component must operate in boiling water, it needs a material with high enough service temperature. If it needs to be transparent, optical clarity becomes non-negotiable. Materials that don't meet this criteria are ruled out immediately. Once the screening is done, the next step is ranking. Here, we need a criterion of excellence, something to teach us which materials perform best under the given design loads. Sometimes that means focusing on single property like low density for buoyancy or low thermal conductivity for insulation. Other times it's combination of properties bundled into what we call a material index. This index helps us compare performance across materials. So in short, screening filters out what won't work and ranking highlights what worked best. The final step in material selection is documentation. This is where we gathered detailed information on the top candidates. It can take many forms: descriptive data, charts, case studies, or visual references. You will find detail on past application, corrosion resistant in specific environments, availability, pricing, and even environmental impact or toxicity warning. This information comes from handbooks, supplier datasheets, digital databases, and trusted websites. Documentation helps refine the shortlist, guiding you toward a final choice that truly matches the design requirements. And this is why the earlier steps, screening and rankings, are so important. Without them, the list of possible material is huge, and diving into all that documentation would be overwhelming. But once you have narrowed it down to a few strong candidates, the search becomes focused, efficient, and effective. So, selecting the right material and process starts by translating design needs into clear constraints and objectives. Through the screening and ranking, we narrow down the best candidates and finalize the choice through detailed documentation. This structured approach makes selection efficient, focused, and reliable. With that, if you are curious about something, comment below or email us. Subscribe to Material Engineer to deep dive into world of material science. Hit the bell icon so you will never miss an update. Until then, keep learning, keep asking, and keep exploring.